There's a single number at the heart of everything we think we know about the universe. Just one. And for decades now, the two best ways we have to measure it keep landing on different answers. Not dramatically different, just off by a few percent. But that stubborn little gap, it's starting to look less like a simple error and more like a crack running through the foundations of modern physics. It's not the disagreement itself that's uncomfortable. Scientists are used to arguing. Honestly, they live for it. The real problem is that both measurements have gotten better and better to more precise, more carefully checked, and the gap hasn't budged. If anything, it's become sharper. That's not what you expect from errors. Usually, as you refine your tools, mistakes shrink away. Not this time. Which leaves us facing two possibilities. Either someone is making a mistake nobody's spotted, or the model that connects these measurements. The very framework that explains how the universe works is missing something big. Keep that in mind, we'll need it. The number we're talking about is the Hubble constant. It tells us how fast the universe is expanding specifically, how quickly galaxies are moving away from each other for every unit of distance. Bigger number, faster expansion. We've known the universe is expanding since 1929, and that's not up for debate. What is up for debate is just how fast it's happening, and, even more unsettling, why the expansion is speeding up. Because it is. That's a fact confirmed back in 1998, and it won the researchers a Nobel Prize. The universe isn't just getting bigger, it's accelerating. Something out there is pushing it apart, faster and faster as time goes on. It acts like an invisible pressure baked right into the fabric of space. We have no clue what this something is. We call it dark energy, which sounds impressive, but really, it's just a label for our ignorance. Dark energy is a flag marking the edge of what we understand. And here's where things get even weirder. The standard cosmological model, the one most physicists use, the one students learn in grad school, the one baked into the software running our telescopes, assumes dark energy stays the same everywhere and everywhen. Same amount in every cubic meter, yesterday, today, and 1 trillion years from now. This isn't because we've seen strong evidence for it. It's just mathematically simple. And, until recently, nobody had clearly proven it wrong. But then, in 2025, one of the biggest cosmological surveys ever finished quietly delivered results that seriously challenged that assumption. The data hints that dark energy doesn't stay constant. It might be changing, maybe even fading away as the universe gets older. And if that's true, the standard model isn't just missing a piece, it's wrong in a fundamental way. We'll circle back to that. But first, let's tackle why measuring the universe's expansion rate is such a pain. Because that's not a side issue, it's right at the centre of the whole thing. The two main ways we measure the Hubble constant come at the problem from totally different angles. One looks way back in time at the oldest light in the universe. The other checks out the more recent universe, using exploding stars as cosmic measuring sticks. If we really understood the universe, both should give the same answer. They don't. The first method uses the cosmic microwave background, or CMB. That's the faint afterglow left over from the Big Bang photons that have been drifting around for almost 13.8 billion years, carrying the story of the universe's earliest days. When scientists study this ancient light with tools like the Planck satellite, they get a crazy detailed snapshot of the universe when it was just 380,000 years old. With that picture and the standard model, they can work out what the expansion rate should be right now. It's not a direct measurement, it's a prediction, an extrapolation, and it gives a specific value for the Hubble constant. The second method is a bit more straightforward. It uses a particular kind of stellar explosion known as a Type Ia supernova. Here's how it works. When a white dwarf piles on too much mass and hits a certain limit, it blows up. The wild part? These explosions reach almost the same brightness every time. Astronomers call them standard candles because of that. If you know how bright something truly is, and you see how dim it looks from here, you can figure out exactly how far away it is. Repeat this trick with lots of supernovae at different distances, and you start to chart how the universe has expanded in the more recent past. This method gives a value for the Hubble constant, a number that tells us how fast the universe is expanding, and this number, it consistently comes out a few percent higher than what we get from the cosmic microwave background, or CMB. A few percent might not sound like much, but in cosmology, it's huge. It means our two most trusted ways of measuring the universe's expansion aren't lining up. And after years of careful, precise work, the gap is still there. That's the Hubble tension, one of the biggest unresolved mysteries in physics. Now, there's a possibility that's tempting at first, and then, honestly, not so comforting. Maybe one method is just wrong. Maybe there's some hidden error in the measurements, and once we spot it, everything will make sense again. Scientists take this seriously. With the supernova method especially, each step of measuring distances relies on the step before it, so if there's a mistake early on, it can throw everything off. People have spent years combing through the data for this kind of error. So far, nothing. Then there's the other possibility, the one that keeps theorists up at night. Maybe our whole model of the universe is missing something. The standard cosmological model, lambda CDM, might not tell the whole story. What if dark energy isn't truly constant? What if the early universe behaved in ways we haven't thought of? Maybe there's some new kind of energy or particle that changed things back then. Any of these could nudge the predicted Hubble constant enough to close the gap. But all of them would force us to rethink what we believe about the universe in a big way. That's why it matters so much to have independent ways to measure the Hubble constant. If a third, totally different method matches the supernova result, it's almost impossible to blame the tension on some hidden error. And actually, there is a third way. It's a bit odd, pretty elegant, and it involves watching the flickering light from cataclysmic events that happened billions of years ago light that arrives at slightly different times. Back in 1964, a physicist named Shure Refstal wrote a paper that pointed out something fascinating. In Einstein's universe, light doesn't move in straight lines. Mass bends space, and light follows those curves. We see this gravitational lensing all the time in the sky. But Refstal noticed something weird about a certain setup. Picture a galaxy sitting between us and some distant, bright object. If everything lines up just right, the light from that distant source takes multiple paths around the galaxy, each path a little different in length. When those paths meet at our telescopes, we see several images of the same object, laid out in a neat pattern around the lensing galaxy. Here's the key insight. Since each path is a different length, the light travelling each route reaches us at a slightly different time. So those images we see, they're snapshots of the same object, but at different moments in its own past. Refstal realised that if you could measure that time difference precisely, and you knew enough about the lensing galaxy's gravity, you could work backward and figure out the real physical distances involved. And at these scales, those distances give you the Hubble constant directly. No calibration chains, no stacking assumptions on top of each other, just a clean, geometric measurement. This approach is called time delay cosmography. Refstal wanted to use it with supernovae. The snag back in 1964 was that we didn't have the tools to catch and track gravitationally lensed supernovae. They're rare, and they don't stick around long. But there's another class of objects out there, brighter and way more common, and it turns out they're perfect for this technique. Quasars are some of the universe's wildest powerhouses. Picture the centre of a far-off galaxy, where a supermassive black hole goes on a feeding frenzy. The stuff falling in doesn't just disappear. Instead, it swirls into an insanely hot disk around the black hole, so bright it can outshine its entire galaxy by thousands or even trillions of times. Even from billions of light years away, we spot these disks as blazing pinpricks. But here's the twist. The black hole's meal isn't steady. Matter pours in at odd intervals, so the quasar's brightness jumps up and down, sometimes fast, sometimes slow, sometimes totally unpredictably. It flickers basically, with patterns that shift from hour to hour or stretch out over months. Now, flickering quasars are cool on their own, but if a big galaxy happens to sit just right between us and a quasar, something weird happens. The galaxy's gravity bends the quasar's light, splitting it into different paths, so when we look through our telescopes, we don't see just one quasar, we see 2 or 4 separate images. Each one shows the same quasar flickers, but they're out of sync. That's because each light path took a different route, and some are longer than others. Maybe image A shows the quasar as it looked 300 days ago, while image B is 400 days old. Same cosmic object, same random blips, just time shifted. If you track the brightness of each image over years and draw out the light curves, you'll notice the same dips and spikes in both, just offset by a fixed delay. That time lag is the difference in path lengths. With some serious math, you can use that delay to calculate how far away everything is, and from there, figure out the Hubble constant, which tells us how fast the universe is expanding. Sounds pretty simple, right? Not even close. There are a few big headaches. First off, the lensing galaxy itself is a nightmare to model. Unlike smooth glass lenses, galaxies are messy billions of stars, gas, dust, and, most annoyingly, dark matter. Dark matter doesn't glow, so you can't just map it out directly. To get a good distance measurement, you need a solid model of the galaxy's gravitational field, which means guessing how the dark matter is spread out. There's no way to check your guesses completely. This is where most of the error comes in. And then there's the mass sheet degeneracy. It's a nasty math problem. You might think you can just focus on the main lensing galaxy, but light from the quasar travels through a cosmic obstacle course, other galaxies, clusters, dark matter structures, all the way here. Any of these can nudge the light, bending it in ways that are almost impossible to tease apart from the primary lens. Miss these extra mass sheets, and your model's off. Sometimes in ways you won't realise until you compare your results to other methods. There's a workaround, but it's tough and expensive. Kinematic measurements. The stars in the lensing galaxy are zipping around inside its gravitational field. By measuring how their light shifts, thanks Doppler effect, you can map the mass more directly, including the dark matter. It's a better handle on the whole mess, but you need long, detailed observations on the world's best telescopes. That only works for closer lensing galaxies, and so far, scientists have managed it for just a small slice of all known cases. The second big problem is tracking the actual time delay. You've got to watch each quasar image, sometimes 2, sometimes 4 faithfully, for years. The catch? Earth's atmosphere gets in the way. Weather, air turbulence, and the fact that these images are crammed incredibly close together make them blur into each other. Computers can help separate the images, but every step adds more uncertainty. And you can't watch the sky non-stop daylight and the sun's position give you gaps, sometimes for months at a stretch. During those gaps, who knows how many flickers you missed? So, measuring the universe with quasars is clever, but it's full of obstacles. Still, people keep at it, chipping away at the uncertainties, because the payoff pinning down the universe's expansion is just too tempting to let go. Pile up all these uncertainties, lens models, mass sheet degeneracy, kinematic corrections, blending, seasonal gaps, light curve fitting, and you end up with some hefty error bars on the Hubble constant for any individual lensed system. So, how do you shrink those error bars? You throw statistics at the problem, more systems, more measurements, more independent lenses to average out the noise. Back in 2019, the H0 Lykow collaboration took 6 carefully chosen lensed quasars and came up with a Hubble constant of 73.3 kilometers per second per megaparsec, with just a couple % uncertainty. Then TDCOSMO, their successor, upped the game more lenses, tighter control over systematics, and landed on a slightly lower number, 71.8. Both numbers line up better with the late universe supernova measurements than with the CMB prediction. They're on the same side of the so-called Hubble tension. But the error bars still loom larger than those from supernova studies. So, taken alone, they don't quite seal the deal. But when you combine them with the supernova data, the whole picture comes into focus. The stats say there's less than a 1 in 10 million chance the late universe and early universe numbers disagree just by accident. 1 in 10 million. That's not noise. That's not some calibration hiccup. That's a real signal. Something's off with our standard model. Still, it's not bulletproof yet. There's just enough wiggle room for some sneaky, systematic error, maybe in the supernova calibration, maybe in the lens modelling, maybe baked into the CMB assumptions, to explain the discrepancy without having to rewrite the laws of physics. The only way to shut that loophole is to bring in even more independent measurements, each with its own unique potential pitfalls. If 3 different methods, each vulnerable to different systematics, all point to a high Hubble constant, then the "it's just an error" excuse doesn't hold water anymore. This is where things get genuinely thrilling. In early 2026, the Vera Rubin Observatory down in Chile will kick off its Legacy Survey of Space and Time LSST. For 10 years, it'll scan the entire southern sky every few nights, building the deepest, richest, most detailed map of the changing sky anyone's ever seen. Right now, astronomers know of a few hundred lensed quasars. Rubin is expected to find thousands, hundreds of lensed supernovae, systems nobody's ever seen before, suddenly getting monitored automatically, night after night, year after year. Combine Rubin's haul with data from the Euclid Space Telescope, which is already out there, mapping the sky in infrared, and you're looking at an expected uncertainty on the Hubble constant, from time delay cosmography of about 1%. 1%. At that level, if the Hubble tension is real, the statistics leave nowhere to hide. The tension becomes undeniable, something that demands an answer. And Rubin isn't just about nailing down today's expansion rate. With enough lens systems spread across a huge range of distances, so a huge range of cosmic times, time delay cosmography, could actually map out how the expansion rate has changed over the universe's history. Not just what's the Hubble constant today, but how has the universe's expansion evolved over billions of years. Why does this matter? Because something happened in 2025 that quietly shook up the field. The Dark Energy Spectroscopic Instrument, DESI, out at Kitt Peak in Arizona, is built to map the universe's large-scale structure with incredible precision. Its main trick, baryon acoustic oscillations, or BAOs, these ripples in the distribution of galaxies that act like a cosmic yardstick, by measuring how that ruler seems to stretch or shrink across different eras of cosmic history. DESI can chart how the universe's expansion has changed from billions of years ago right up to now. In 2025, DESI dropped its first big results, and they hit like a thunderclap. They pulled together their BAO measurements, CMB data, and supernova observations. The combined data told a story nobody really expected. Dark energy isn't holding steady. Its density has changed. As the universe ages, it's actually getting weaker. In the early universe, dark energy was stronger. Now, not so much. That flies in the face of the standard model, lambda CDM, which insists dark energy is a fixed feature of space, steady and unchanging. DESI's results say, not quite. If dark energy is changing, then the so-called cosmological constant, Einstein's old term, for this strange energy isn't really a constant after all. And that blows a hole in the foundation of the standard model. At best, we need to revise our physics textbooks. At worst, we're looking at a whole new kind of physics. So, what is dark energy, really? What creates it, and what could make it evolve over time? Getting to the bottom of that might mean we need to understand physics at energies we've never even come close to reaching in experiments. It could also mean we finally have to make general relativity and quantum mechanics play nice, something that stumped everyone so far. Or maybe it's something completely out of left field. There's hope though. Time delay cosmography, especially with help from the Rubin survey, could let us track how dark energy changes with the kind of detail we need to actually test different theories. Each model for dynamic dark energy predicts its own unique pattern for how the universe's expansion rate should evolve. If we map that out well enough, we can start crossing off theories that don't match up. We can finally move from just describing what dark energy does to actually figuring out what it is. Let that sink in. Since 1998, we've known that about 68% of the universe's energy is something we can't explain, can't see, can't poke in a lab, and can't derive from first principles. For nearly 3 decades, it's been a glaring hole in our understanding of reality. And now, the best shot we have at solving it comes from the faint, delayed signals of some of the universe's wildest events, quasars brighter than entire galaxies, their light bent by gravity, taking different paths across billions of light years, and arriving at Earth with just a slight difference in timing. Hidden in those tiny delays is a clue about the shape and story of the entire universe. Now, let's talk about that supernova from 2014. While scanning Hubble data, astronomers spotted something weird. A distant galaxy acted as a lens, and around it, 4 faint dots appeared the same supernova shown 4 times. The explosion's light had travelled for over 9 billion years, then bent around a galaxy cluster and landed, a little smeared and duplicated, in Hubble's view. The scientists crunched the numbers, modelled the lens, and made a call. A 5th image, taking the long way around, should show up about a year later. So they waited. They aimed Hubble at the spot, and, right on time, there it was. That event became known as supernova Refstal, after the physicist who dreamed up this technique 60 years earlier. Its time delays gave a measurement of the Hubble constant. Then, a more recent lensed supernova SN H0PA, a type Ia, just like the classic standard candle supernovae, gave 2 independent Hubble constant measurements from one object, one from the lensing time delay, one from how bright the explosion was. Both lined up with the high values we see in the late universe. Both added to the ongoing tension. Sure, the uncertainties on those 2 supernovae are bigger than what we get from quasar studies. But that's just what happens when you don't have many examples yet. Rubin is expected to find hundreds more lensed supernovae, and as that sample grows, those error bars will shrink. Plus, Type Ia-lensed supernovae are a goldmine because they let us combine two different measurement methods, lensing and standard candles in a single object. That kind of cross-check helps us calibrate the numbers in a way neither method can do alone. So here's where things stand. The universe is getting bigger, and it's doing it faster and faster. The weird part? When scientists measure how quickly it's speeding up, they keep getting different answers. And even after years of fine-tuning their tools, no one's been able to explain why. The latest evidence points to dark energy, the thing that's supposed to be pushing everything apart, not being the simple, steady feature of space we thought it was. Now, it looks like dark energy might be something wilder, more unpredictable, and a lot stranger than physicists expected. For the first time, though, we're about to get the tools to actually start answering these questions, not just ask sharper versions of them. The Rubin Observatory is about to shake things up. Where we used to spot hundreds of lensed quasars, now we'll see thousands. Lensed supernovae, which used to be basically invisible, will pop into view. The observatory will watch these things for 10 years straight, collecting data that'll finally let us measure their time delays with crazy precision. When you add in the data from Euclid and all the follow-up work from ground-based telescopes, the numbers around the Hubble constant and how dark energy changes are going to get tighter by a lot. We're not talking decades away, either. By the end of this one, we could know if the so-called Hubble Tension is a sign that physics itself needs rewriting. We could find out if dark energy isn't constant, and if it's changing, exactly how and how fast. That would finally give us a real shot at figuring out what the universe is actually made of. But there's a bigger question hiding behind all of this, something none of the data has touched yet. If dark energy really does change over time, if it used to be stronger and is now fading, then what happens next? Does it just keep fading? Does it ever hit zero? Could it even flip and go the other way? What happens to a universe where dark energy evolves? Maybe it stops expanding one day, or even starts to shrink. The standard model says the universe will just keep spreading out forever, getting colder, emptier, until nothing new ever happens again. But that's only true if dark energy never changes. Take that assumption away, and the future becomes anyone's guess. This isn't just wild speculation. It's what the evidence is actually saying. If what DESI is seeing turns out to be right, if dark energy is dynamic, then the story we've been telling ourselves about the universe for 20 years could be flat out wrong. Not just in the small details, but in the big stuff. Does the universe expand forever or not? Are galaxies and cosmic structures doomed to drift apart, or is something more complicated going on? And all of that comes before we even tackle the toughest question at the heart of this story. Dark energy makes up about 68% of everything out there. Dark matter is another 27%. The rest? That's all the atoms, stars, planets, and particles we've ever seen or put in an equation. Just 5%. We actually understand that 5%. The rest, well, we've given it names, but that's about it. If the Hubble tension means we need new physics, it's not just about tweaking an equation. It means the whole framework might be missing something big. And whatever dark energy really is, how it works, why it changes, could be tied to questions that go way deeper than just cosmology. We're talking about the energy of empty space, the nature of quantum fields, why the vacuum is the way it is. These are the same mysteries that get at why matter exists at all, why the universe's constants are what they are, and if they ever used to be different. We're stuck on a disagreement a few percentage points between two numbers. And behind that, just barely visible, there's a darkness that might cut all the way down to the most basic rules of reality. If there's an answer, it starts with watching for the echoes. There's still one more thing in the data that people haven't really grappled with. If dark energy is fading, if it's on its way down, then you have to wonder, what came before? Why was dark energy stronger in the past? Was there a time before this current era of acceleration when something else was going on? And if it keeps fading, does it link back to something that happened in the earliest moments of the universe, before the cosmic microwave background, before nucleosynthesis, before even a split second after the Big Bang, when everything was governed by rules we've never observed and can barely even imagine? That's the next frontier, the very early universe. And honestly, we haven't even scratched the surface yet.